Good morning, students. Today we are going to do a new chapter, that is kinetic theory of gases. We have already discussed about the basic nature of solids, liquids and gases. In solids, molecules are densely arranged. The intermolecular force of attraction is very less. Whereas in liquid, intermolecular force of attraction is intermediate. Solids, the force of attraction will be maximum, so that the molecules are densely arranged. There is no intermolecular space. But when we deal with gases, the molecules are widely separated. The molecules are free to move. Their intermolecular force of attraction is very less. So the gases does not have definite shape, they does not have definite volume. If I take a gas in a container, the gas can occupy the entire volume of the container. So here in this classroom, there is air. The air is occupied through this entire space, the entire volume. If I want, I can take all this air and compress that into a water bottle. Compress it in a water bottle. So the density will be high. So the gases are highly compressible, but when you open that bottle, the gas will just go out from the bottle and it will spread the entire space. So that is the nature of the gas. So in this section, we are going to deal with certain gas laws. The first law is Boyle's law. Boyle's law states that at constant temperature, the volume of a given mass of gas is inversely proportional to the pressure. The volume of the given mass of gas is inversely proportional to the pressure. So we will write like this: V proportional to 1 by P. Volume is proportional to 1 by P. Or I will write PV is equal to constant. Therefore, P1 V1 is equal to P2 V2. So if I draw a graph connecting pressure and volume, when volume increases, the pressure will decrease, and when volume decreases, the pressure will increase. So the graph will be a curved line like this. Okay, so you can take down the statement of Boyle's law. At constant temperature, the volume of a given mass of gas is inversely proportional to the pressure. So after that, just copy these things and then the graph. Now let us move on to the second law, that is Charles' law. Charles' law states that at constant pressure, the volume of given mass of gas is directly proportional to absolute temperature. So for Charles' law, what should be constant? Pressure. In Boyle's law, what was constant? Temperature. Okay, in Charles' law, pressure is constant. You can take down the statement: at constant pressure, the volume of a given mass of gas is directly proportional to absolute temperature. So I will write like this: volume proportional to T, or V by T is equal to constant. Therefore I can write V1 by T1 is equal to V2 by T2. So here what I say is, when temperature increases, the volume of the gas also increases. When temperature decreases, the volume of the gas decrease. So when I draw the graph connecting the temperature and volume, when I take the graph connecting the temperature and volume, the graph will be a straight line. You can see here I am not drawing it from the origin, I am drawing it after some distance from the origin, because in the normal sense we can't make the temperature to 0. 0, what I mean is 0 Kelvin. The minimum possible temperature that we can attain is called absolute 0 or 0 Kelvin. That is why we are talking about absolute temperature. Simply if I say temperature, it can be temperature in degrees Celsius or it can be temperature in Kelvin. But when I say absolute temperature, that means temperature in Kelvin. So I am just putting dotted lines here. That means when I extend the graph, when the temperature becomes 0, that means 0 Kelvin, the volume of the gas becomes 0. And I can't make the temperature below 0, because if I try to make the temperature below 0, the volume of the gas becomes negative, which is not possible. That's the reason. Okay. Now the third one is Gay-Lussac's law. Gay-Lussac's law. It tells that at constant volume, pressure of a given gas is directly proportional to absolute temperature. At a constant volume, the pressure of given mass of gas is directly proportional to absolute temperature. That means when we increase the temperature, the pressure will also increase. Therefore, we can say like this: P proportional to T, or P by T is equal to constant, or we can say P1 by T1 is equal to P2 by T2. So if I draw a graph connecting temperature and pressure, as we told just now, the graph will be a straight line. The graph will be a straight line. So here also I just put dotted lines which comes to the origin. That means when the temperature is 0 Kelvin, the pressure of the gas will be 0. So that means 0 Kelvin or absolute 0 is the condition, is the temperature where the pressure of the gas becomes 0 and the volume of the gas also becomes 0. Okay, now based on these laws, we are going to derive the ideal gas equation. So, ideal gas equation. We already studied volume proportional to 1 by P. Pressure is inversely proportional to volume. And then we studied volume is directly proportional to temperature. So when I combine these two things, when I combine these two equations, I can write volume proportional to T by P. Or I will write PV by T is equal to constant. So I will write PV by T is equal to, that constant is called R, where R is universal gas constant. R is universal gas constant, and the value of R is 8.31. joule per mole per Kelvin. Joule per mole per Kelvin. Or I can say one more equation. This is in the SI unit, and in CGS unit you can take the value as 2. Calorie per mole per degree Celsius. Calorie per mole per degree Celsius. Actually it is 1.98. I am rounding off this as 2. The correct value is 1.98. I just round off this as 2. Okay, 2 calorie per mole per degree Celsius. So I can write PV is equal to RT. This is for 1 mole of gas. You can take down these things. Now PV for n moles of gas, PV is equal to nRT, where n is the number of moles. So this is the ideal gas equation. PV is equal to nRT, and we have studied the value of the universal gas constant, that is 8.31 in SI unit and 2 in CGS unit. Now the next thing is Boltzmann's constant. Boltzmann's constant is denoted like this: Kb, K subscript B. It is the gas constant. Boltzmann's constant is the gas constant per molecule of gas. Boltzmann's constant is the gas constant per molecule of gas. So we can say like this: Kb is equal to gas constant by Avogadro number. When we divide, this gas constant is for 1 mole, 8.31, that value is for 1 mole. I want gas constant per molecule. So what should I do? Divide that by Avogadro number. So Kb is equal to R by Na, where Na is the Avogadro number. And the value of Na is 6.023 into 10 raised to 23. Mole raised to -1. So when we give that value, Avogadro value here, I will be getting the value of Kb as 1.38 into 10 raised to -23 joule per Kelvin. 1.38 into 10 raised to -23 joule per Kelvin. This value also you have to learn by heart. So that's all about this topic. Thank you.